My talk is measuring complexity with simulations. And so we really like measuring things in this. Here's an example of our several generations outdated meter standard. And I think it's kind of similar with measuring complexity in the sense that in the end you have to have some basis, some sort of standard meter stick that you compare against. And different people may make slightly different choices of what that standard should be, which ultimately may be a little bit arbitrary. But what I'll think of as the standard as being a quantum circuit model with some particular gate set, such as, say, Hadamard sitting on the T, or maybe topically in Hadamard. I think Scott mentioned some universal gate set, and counting gates is our measure of complexity for some computation that you want to do. But it's a little bit different than a meter stick in the sense that it seems to me you really get upper and lower bounds on complexity rather than just some single number, because the way you compare two things together, instead of just laying them side by side, you can try to simulate one with the other. So if you have some physical system, some dynamics, and you say, well, we can simulate this using such and such number of gates in this standard circuit model, then that sets an upper bound on how much computational complexity is contained in the dynamics of this system. And to get a lower bound, you can say, well, if this system is computationally universal, you could take some arbitrary circuit of such and such number of gates, and whatever is the maximum number of gates or an arbitrary circuit that you can simulate with that system, whose output you can encode in the final state of that system, then that sets some lower bound on the complexity. So really, in this talk, I'll give two examples of this. The talk is kind of in two parts. The first part is something that was a lot of work and very technical to show, but maybe the outcome is something that will be not too surprising. And the second half of the talk was something that was fairly simple, but perhaps much more surprising or infuriating or exciting or something, I hope. So, okay, so let's survey sort of state of the art. So one thing that people have sort of noticed when kind of measuring complexity of all different things is that they've never found a physical system, to my knowledge, that really seems to be able to do things that are exponentially more computationally powerful than what standard quantum circuits can do. Now, of course, 30 years ago, people might have said the same thing about, or maybe 40 years ago, people might have said the same thing about classical Turing machines, but now they say that about quantum circuits. So there's kind of this hypothesis, which might be called the Church-Turing-Deutsch thesis, or some people would call it the quantum Church-Turing thesis. But anyway, basically what it suggests is that quantum circuits can simulate all physical dynamics in some number of gates, which scales only polynomially in the energy, space-time volume, and precision that you want to simulate. So this is actually a very far-reaching and bold claim, and I think it's a very interesting question to investigate whether it's true. So we have to think about different physical systems we know about and whether we can simulate them efficiently. And so for sort of undergraduate type non-relativistic quantum mechanics, this is pretty well understood at this point. We have rather general quantum algorithms for simulating the dynamics of these things. And I'd say that at this point, the main research question is, okay, we know we can do this in polynomial time for specific systems. Let's try to do it better and better, fewer gates, fewer qubits. So then we can look at, well, relativistic quantum systems. Maybe in principle these might be different. Particle number is no longer conserved. And in principle, the number of degrees of freedom in some finite region of space-time is naively infinite. And so you could ask, well, it's not an obvious corollary from these non-relativistic quantum mechanics simulators that you can also simulate quantum field theories efficiently, because if something's just running in time polynomial in the number of degrees of freedom or in the number of particles, then that's not directly and obviously enough. And so this is something that I've been working on for a few years in collaboration with John Preskill and Keith Lee, and more recently sort of looking at the lower bounding question, also in collaboration with Hari Krovi, added to our group. But what we have so far is that in the examples that we've so far considered in detail, it does appear to be the case that with polynomial number of quantum gates and qubits, we can simulate the dynamics of these sort of simple first examples of quantum field theories that we've looked at.
Gauge theories?
We have not looked at gauge theory. So basically, we went to the simplest kind of textbook models we could find, which were massive 5/4 and massive gross nebula model. So just bosons and fermions, not even massless particles, just the very bare minimum we could look at. And it was already, because we were interested not just in sort of broad arguments about can it be done in polynomial time, but really laying out in detail the full algorithm, including state preparation, measurement, exactly what the scalings are, what polynomials are. That's kind of the approach we're taking, sort of looking at simple examples. And of course, maybe the final question, the most the most serious challenge to this Church-Turing thesis probably comes from quantum gravity, and I would say the present state is nobody knows whether this is a violation of this thesis or not, which is not to say that nobody's ever thought about it or written papers about it. Here's one I would like to mention with Adam Bowen, who's here, and Ning Bao, talking about whether certain models of black holes would imply greater computational power or not. But that's sort of a side issue. The first part of my talk will be really about this. Okay, so if we want to be sort of responsible complexity theorists, we have to fairly precisely define what is the computational problem that we want to solve. And so the problem that we chose, not necessarily the unique choice, but I think a very natural choice, is computing scattering probabilities. And so the input to this problem is basically a list of momenta of incoming particles, and the output is a list of what particles come out from this scattering process and what their momenta are, basically. We can also have some spatial information about where they are as well. So I think this is a fairly natural problem. I think if you're a theorist, you'd say, well, this is basically a S-matrix calculation problem, something very familiar. And if you're an experimentalist, I feel safe in saying this in this crowd because there probably aren't in here. But I think that experimentalists would say, well, at least this is some cartoonish, simplified version of the kind of things that you would really measure in a particle accelerator. And one thing I should note about this is if you demand, you have to be careful about these definitions. Because if you demand, for example, that the quantum computer write down the probabilities of all the possible outcomes, even just writing that down might take an exponentially large number of bits. So you don't demand that. What we demand from the quantum computer is to sample from the same probability distribution over outcomes that quantum mechanics, that quantum field theory itself produces. So it's the way the data comes out is the same way it would come out from an experiment. Okay, so just to skip to the punchline of the first half of the talk, our results so far are in two examples. We looked at a theory with only bosons, a theory with only fermions, and we considered the case where the particles were all massive. And there are some things on the to-do list that we have some ideas about how to extend our algorithms, but these are the cases we looked at in detail.
Did you do only super renormalizable things?
Well, so 5/4 theory in 3+1 dimensions we also considered, and it's just an effective theory, but the story is cleanest in these super renormalizable cases like 2+1 and 1+1. We especially liked working on those. So then this is basically the punchline in terms of upper bounds on complexity. And our most recent work is actually about the other side, lower bound. Taking a universal quantum circuit and encoding the, say, all zeros bit string to all zeros bit string transition amplitude of that circuit into some corresponding transition amplitude of a quantum field theory. In this case, it's the vacuum to vacuum transition amplitude of 5/4 theory with some space-time dependent source term, which encodes the circuit that you're trying to simulate. So I think the interesting thing about this is that this was already, first of all, a weakly interacting quantum field theory. It only had one species of particles, which were bosons. They were massive. And it was only in 1+1 dimension. And already in that case, there is sufficient richness to encode universal quantum computation.
When you say formal evidence, you actually do mean deeply parsed.
Yeah. I should say that essentially none of the things that I will talk about in this first half of the talk are proven with absolute rigor of like mathematician quality, but it's sort of at an intermediate level between a typical physics paper and a fully rigorous math paper. We do have some arguments which are sort of mathematical physics style, I guess I would say. But okay, so I'll just go through an example in detail to give you an idea of what are the interesting issues that we found to arise in developing quantum algorithms to simulate quantum field theories. And actually, it turned out that a repeating pattern was that the issues which seemed to be kind of grungy details that would be kind of technical and annoying in some sense were actually turning out to be the most interesting aspects. So you'll see what I mean here. So our main example, the one I'll tell you about today, is 5-4 theory. So here's like our Lagrangian standard one, non-zero bare mass. And for quantum simulation, we just prefer to think of it in a Hamiltonian formulation because it just maps more directly onto existing quantum simulation algorithms. So then we have some Hamiltonian, which in principle is continuous in space with canonically conjugate operators associated with every location. And so, of course, the thing to do is then discretize this and reduce it to some kind of many-body quantum mechanics problem, a set of coupled anharmonic oscillators, exactly as Rob Myers described this morning. So that's the basic idea. So first of all, how are we going to represent quantum fields on our quantum computer? So once you discretize space into some kind of grid, then the field will reduce to just a list of numbers, some values, the value of the field at each of these grid points. And each of those values can be approximated by writing down bit strings with some number of bits of precision. So now the configuration of a classical field is just a long string of bits. And of course, a quantum field is some arbitrary superposition over different classical field configurations. And so correspondingly, our representation of that on a quantum computer will just be superpositions of those corresponding bit strings. And superpositions of bit strings is exactly a state of quantum memory, a set of qubits. So what are the challenges here? So the basic challenges are, one, we have to choose some discretization and try to bound the discretization errors. This is the first example of something that sounds like some kind of grungy details that are not interesting, but in the end it really ends up to be a question about renormalization group flows, and which of course are one of the really key exciting features about quantum field theory that make it different and more and richer than kind of undergrad quantum mechanics. The second challenge was, well, you're not just given some initial state, you need to do the state preparation problem. You need to prepare even a free vacuum. You need to prepare starting from qubits. Then you need to prepare interacting vacuum. You need to make particle wave packets on top of that. All of that costs gates and qubits, and you need to figure out how to do it efficiently with polynomial resources. And then the middle step is just simulating the time evolution of these things. That's actually kind of the easiest step because, as I said, once you discretize this is just some system of coupled anharmonic oscillators. You can apply the old quantum algorithms for simulating systems of finitely many degrees of freedom that were developed many years ago by like Zalga and Lloyd and so on. So this part is kind of a solved problem. We basically apply standard known quantum algorithms tricks more or less right out of the box, just with a few optimizations to take advantage of the efficiency gains you can get from the locality of the interactions. And the last step is you need to perform some kind of physically informative measurements on the final state. And, well, this line I write here about is complicated by vacuum entanglement. That's a little bit speculation on my part. What we know is that certain naive ways of doing these measurements, which seem like very obvious things to try, actually don't work. And I believe that underneath it, it really has to do with the entanglement of the method. But I'll explain precisely what I mean later. Okay, so let's just kind of go through these things sort of one by one. So first of all, discretization errors. So we're going to work, as I've said, with lattice cutoffs. And we can think of, conceptually, our continuum quantum field theory as some continuum limit of a sequence of lattice field theories. We have some lattice Hamiltonians on each lattice. And we try to take the limit of this. And as most people here know, to get this to work, to get this to yield a continuum limit, first of all, it only rigorously works, it only really works in these like in these 1 plus 1 and 2 plus 1 examples. But also you have to tune these parameters in your lattice Hamiltonians in a very careful way to make sure that you really converge to a limit and that the limit you converge to is not just the free theory. It's actually something interesting where the particles are interacting with each other. So you can also, of course, view this process the other direction. You can start with a theory on some finer lattice, integrate out, in some sense, some of the degrees of freedom, and obtain some effective theory, some Hamiltonian describing the dynamics on a longer length scale by some corresponding effective Hamiltonian on this coarser lattice. And what you do, when you do that, you'll find that your new Hamiltonian, in these examples, essentially looks very much like your original Hamiltonian, except that you'll have some adjustments to your parameters in there, the mass parameter and the sort of interaction strength parameter. This is kind of like following those flow of these other parameters in the opposite direction. But on top of that, you'll also have these small correction terms with all sorts of higher order things in here, phi 6, higher powers of phi, things involving derivatives of phi. And these things really are a signature of how much error you're inducing by doing this discretization in the first place and not taking the lattice cutoff all the way to 0 lattice spacing. And so you can analyze how these parameters scale. You can look at it by dimensional analysis, or in the perturbative regime, you can calculate them explicitly. And in both cases, you find that the things that are disappearing the slowest as you take this lattice spacing smaller and smaller are vanishing in the number of spacetimes that we looked at quadratically with the lattice spacing. So that's pretty good convergence. Even if you're making classical algorithms, quadratic errors as a function of lattice spacing is a pretty typical thing to achieve for practical algorithms. So that's sort of what I want to say about the discretization errors. You know, it's this kind of grungy thing, oh, who cares about discretization, but in the end it's really about renormalization, which makes it seem more exciting. So the second issue I mentioned was, what about state preparation? So our strategy in these papers was, well, let's start from the free theory. The nice thing about the free theory, when you turn this interaction parameter lambda all the way off, then the ground state is a Gaussian, just as Rob Myers mentioned this morning. And we know how to make Gaussian superpositions efficiently, which is to say in polynomial time on quantum computers. So then the question becomes, once we've made those Gaussians, how do we get from there to the states that we want of the interacting theory, which is basically vacuum plus a few particles on top, say 2 particles. So our strategy was, well, let's do that adiabatically. If we're in the phase of the quantum field theory that's connected to the free theory, we should be able to reach adiabatically. That's not to say we use different hardware, some adiabatic quantum computer. We just say, well, there's an adiabatic process by which the state can be prepared. We simulate that using our quantum circuits. So we have some parameter. We put it in front of the interaction term in our Hamiltonian. We slowly vary that parameter from 0 to 1. So if we start by making the wave packets in the free theory, and then we do this adiabatic preparation, that sort of almost works, but there's a problem with it. And the problem is that we're not trying to prepare an eigenstate. We're trying to prepare wave packets, which are superpositions over different eigenstates. And so these different elements of the superposition will acquire different phases because they have different energies. Or a more physical way to put that is, well, time evolution is happening. These wave packets will evolve. When wave packets evolve, they propagate and they broaden. And both of those are bad for us, because if they propagate and the particles collide before we've got S all the way equal to 1, then we're simulating a more weakly coupled theory than we intended to. And also, if we have very broad wave packets, then these packets are very diffuse. So even if they're sitting right on top of each other, the expected distance between the particles is not small. And so our probability of having non-trivial, sort of non-identity type parts of the S matrix, these sort of non-trivial scattering processes, is going to be lower.
But is it possible to turn on the interaction and create a vacuum then?
Yeah, so that's what we did in our second paper, the one about fermions. And in some ways, that ends up being a simpler protocol, but it has its own challenges too. So I can tell you about that one as well. But what we came up with was kind of a funny trick, because remember, this is a simulation. It's not real physics, so we can do bizarre things. And one of the bizarre things that ability we have, which we took advantage of, was the ability to run time backwards. And so what we can do is we can do forwards time evolution as this coupling constant is gradually increasing, which does this adiabatic change of basis. And then we do backwards time evolution with constant value of the coupling, which kind of undoes the dynamical phase without changing the basis. And so we have this kind of zigzag path. Here's coupling strength versus time. We sort of go backwards in time and forwards while increasing coupling strength backwards and forwards. Make this little zigzag. And we can show that if you make these little zigzag pieces smaller and smaller, sort of finer sawtooths here, it converges to doing just what we want. So that's our little trick, which might be useful for some other state preparation problems. And the last piece, before I move to the second portion of my talk, is, of course, the final part, which is measuring what you've got at the end of this simulation. So one of the things you might want to do is detect, where particles have ended up and what energies they have, maybe if they form some bound states, what the energies of those are. So one of the things we thought about measuring is, well, what if we sort of divide space into little pixels and try to measure the energy in each one, some kind of cartoonized version of a detector. We know how to measure any observable we can simulate the time evolution of. We can measure in the eigenbasis of that observable using the space estimation algorithm. So the naive thing to do is, well, okay, H is some lattice Hamiltonian. It's the sum of terms summed over different lattice sites. So let's just truncate that sum to some region. Let's measure that observable. Well, this turns out to be not the right idea, because when you look at what the variance of that observable is in the vacuum state, that turns out to be ultraviolet divergent. And that's very bad, because you're trying to measure this small energy from a particle being there versus not being there. If that's against this gigantic noise background, you have a big signal-to-noise problem. You're not going to notice it. You won't be able to distinguish it.
Is it because of the sharp edges or?
Yes. So then what we did, instead of just truncating the sum, we put an envelope function on there with nice smooth edges like a Gaussian, and things seem to work out okay. I think maybe this, so those are we've done the calculations and I'm telling you something true part of this slide. And then my speculative commentary is, maybe it has something to do with vacuum entanglement, the fact that, well, if you look at some region of the vacuum, that's some highly mixed state, and so it's not surprising that lots of things that you measure on those states can be very noisy. Okay, and then just to summarize the runtimes, so these are runtimes that are polynomial, and then the actually hardest, most time-consuming step is the state preparation. The red is the cases where the most time-consuming step is the preparation, the adiabatic part, and this purplish color is actually preparation of the Gaussian free vacuum. Although I have recent work in collaboration with Rolando Soma that improves these numbers and makes them no longer the dominant cost.
Do you have an easy way to prepare composite states?
You mean like bound states of multiple?
Yeah.
Well, so one thing you could try doing is you could, this is sort of the approach you were looking at in our fermion paper, prepare the interacting vacuum adiabatically, and then create particles on top of that vacuum by simulating some kind of sinusoidally oscillating source term. to sort of resonantly kind of Rabi oscillate particles out of that vacuum. And so that might be more applicable to generating bounce states, although we haven't really specifically worked through it.
So when you said state preparation is the costly one, is it the back and forth part or is it?
Yeah, that's the part. So any of these things, these red boxes, it means the slowest part of the algorithm is doing this whole thing.
So can't you prepare a sort of more diffuse, so broader state and just focus it to begin with?
Well, so, I mean, there's alternative things you could do. Like you could say, well, maybe these things are propagating towards each other, but just make the space bigger, have these big runways. Then it's very costly in terms of qubits, and it starts adding up, so it's not so easy to improve this. Now, I have current work with a graduate student looking at ways to use matrix product states and things like that to do more direct creations of these actions. So that's kind of ongoing. But yeah, state preparation seems to be the bottleneck right now.
But if you could create the vacuum, can't you measure correlation?
Yeah, you can do that. You don't have to do scattering processing. You can just
Well, you can read out the scattering process and correlations. That may not be easy.
yeah. Well, I think so. If you have like noisy measurements of like, okay, let's put this operator here, let's put this operator here, measure that correlation function to within plus or minus epsilon, and you start collecting data points like that, and then you want to use that data to extrapolate scattering cross sections. There might be some sensitive, kind of like numerical sensitivity issues. Yeah.
Sorry if this is naive, but can you explain why there's such an asymmetry in the in and the out state when you discuss the preparation states on a very different footing?
Yeah, well, so we actually wrote two sections in our paper. One where the final measurement is just a time inverse version of this. So we go back to the free theory and measure number operators with individual modes, and then we're getting pure momentum information. So that's another thing you can do, but then you might lose track of bounce states and stuff.
I just would have thought that, I mean, if you can prepare any end state, sorry, is the question whether you can prepare any state that might come out? Is that where the asymmetry comes from? That there might be stuff coming out that you couldn't have prepared? Otherwise, you could just like take an inner product with the stuff that
Oh
you
yeah,
not prepared.
right. But I think the problem with that is like any individual state you would prepare is quite likely to have very small probability. And so it's more like, well, you sample from this distribution and you start building up some histogram, whereas instead you just start asking, did we land in this box? And you ask that over and over. It might take you a long time before you see an example that's yes. But you could do that. All right, so that's part one. This is kind of this part is about asking, are there systems where by taking advantage of a richer set of kind of primitives, physical primitives, can we get shortcuts? Like if we use a more general gate set, do you need fewer gates? If we use something physically richer like relativistic quantum field theory, does that mean you need asymptotically smaller amount of resources? Especially the question is, are there any examples where there's an exponential separation in this game?
Isn't quantum field theory more restrictive than quantum mechanics? No, that's
Well, you could also think about it that way, because you could say, well, now you've added an extra symmetry constraint. It has to be Lorentz invariant, and then that's sort of restricting rather than broadening. I mean, it depends exactly how you do it. So, like, it is more restrictive in that sense, but on the other hand, you kind of have to worry about this. Well, if you had some quantum field theory process, could you tune it in some special way that the outcomes are somehow sensitive to very UV degrees of freedom, and then simulating those might be super costly. That's kind of the main thing to the question in some sense. Yeah.
But even classically, you might have worried about chaotic behavior.
Yeah, people still do worry about that. I think there's a recent paper by Terry Tao looking at some kind of simplified version of Navier-Stokes and asking whether you can make some initial conditions that produce self-replicating robots that become exponentially small and So, yes, there is such a question.
I think, you know, he actually proves you can do that but for a different version of it, like without this concept.
Yeah. So, anyway. All right, so what I've said before is kind of about shortcuts. Well, let's say, okay, forget about shortcuts. Let's suppose there are no more shortcuts. Quantum mechanics was the only one. BQP, the things you can solve in polynomial time with quantum computers, is the end of the road as far as that goes. But then there's a second question, in some sense a finer grained question you can ask. Okay, we know how many steps we need, and we just do them faster and faster and faster. That's how we save time. You know, we've had this, things have been speeding up for 50 years exponentially. You know, what are the limits? What are the ultimate physical limits that might, you know, stop us in our tracks as far as getting faster computers? That's yeah. Yeah, well, so that's one of the things that people first talked about. So like, one of the ideas was, well, people thought that with every operation you do, you need to dissipate like kBt of energy in the form of heat. It was eventually realized by Landau that this really applies just to deleting, erasing information. And we now know from Charlie Bennett that you can do all your computation.
I'm not talking about erasing, just to
Yeah.
make things happen fast.
Okay, so that's what this part, this is the hopefully contentious and interesting part of my talk. So this is about that. So after Charlie showed that we could do things without spending energy at every step, there's still a remaining question, like just how much energy does there need to be there in the first place, even if you're doing your computation kind of ballistically without dissipating energy along the way. And there have been arguments along these lines. So one of the intuitive arguments was, people say, well, there are various energy time uncertainty principles, and they say something about how if your spread in energies is delta E, then your uncertainty in time, delta T, has to, you know, the product of those two things have to be at least Planck's constant. And if that's the case, then maybe that sets a limit to computation. Because if you make your time in between operations smaller than this uncertainty in their timing, then they might be out of order. And so presumably that ruins everything. And so people would say, well, maybe the maximum clock speed of a computer is Planck's constant over your uncertainty in energy of your system. That might be one of them. And there's kind of a more quantitative version. There's this theorem from Mandelstam and Tam, which says that to go from a given state to an orthogonal state, the fastest you can do that is given by h over 4 times the uncertainty in energy. And so you think, okay, well maybe this gives you the shortest time in which you can do a logical operation. Certainly, it definitely is the shortest time that you can flip a bit from 1 to a 0. So it seems like it stands to reason that if you want to do, you know, G logical operations and it takes this much time to flip a bit, then maybe it takes G times this much time to do your operations. In classical computing, every time you apply a gate, you flip at least 1 bit, otherwise the gate was rather pointless. And in a generic quantum circuit, each time you apply a gate, you're hopping to a near orthogonal state. So it kind of seems pretty plausible, maximum clock speed being proportional to delta. And there's another version of this theorem which says, well, suppose you're Hamiltonian, we set the zero of energy at the ground energy of Hamiltonian, and it says that the minimal time to flip a bit is h over 2 times the expectation of the value of energy of your system. And so this would say the maximum clock speed should be proportional to this expectation value of energy. So as plausible as these arguments sound, they're not really correct. So it's not really a limit, and there is a way of circumventing this, somewhat surprising. You can actually do your entire computation to within a constant factor of the same amount of time as it takes to flip a single bit. Quantumly, you can do this. And so how could that be? So first of all, if you think about a standard quantum computation, you start your starting state and your final state. At worst, they're orthogonal. So they're not far apart in any real sense. It's kind of independent of how many logical steps it takes to get from one to the other. But what you do to get there is normally you apply a bunch of gates and you bounce all around the Hilbert space to a whole bunch of near orthogonal states and finally end up at your target. But maybe there's a way of going more directly. through Hilbert space while still restricting yourself to physically realistic operations that are, geometrically local and everything like that. The other thing you'd say was, well, and that's kind of how this construction will work that I'll show you. And the other thing is, well, what about this other argument about the uncertainty in timing making the operations out of order? And sort of the loophole there is that the uncertainty in this construction in the timing of any individual operation is very large, but these are all correlated with one another so that the ordering of them is completely certain. And so now here's the paper about this. It's also on the archive. It's pretty recent, and I'll show you what it does.
But are you saying merely that the Margolis-Levitin type of argument for the computation speed is wrong, or that you can actually do like arbitrary number of steps in whatever one time or whatever it might be?
I'm not saying the latter, because what I'm saying is that you can make constructions which are, in most respects, look very physically realistic, where the ratio of clock speed to energy is as high as you want. But ultimately, there could be other sources of limits, such as maybe there's some limit to how densely you can pack qubits, and then if the qubits are this far apart, it takes this long for light to go from here to here, and therefore it takes that long to do a 2-qubit gate, etc. So the argument is, from these counterexamples I'll show you right now, is that energy alone is not enough physics to tell you a limit on computation.
So in some sense, you're really looking at quantum gravity then.
Yeah, maybe.
Yeah. Okay.
So here's how the constructions work. The basic underlying trick is, in some sense, literally the oldest trick in the book in quantum computation. It's Feynman's an adaptation of Feynman's original design for a kind of ballistic quantum computer. And so again, I'm using this simulation yardstick. So I start with some quantum circuit, and I'm going to say, well, here's how we can simulate that quantum circuit using a time-independent Hamiltonian where all the energies are small and the spreads in energies are small. And so we start with our quantum circuit, and then we write down, as our first step, a Hamiltonian like this. So this is really Feynman's Hamiltonian. We introduce a new register, which we call a clock register. And these are the original, this is a gate from the teeth gate from the original circuit, and here's this complex conjugate. So this is some kind of hopping Hamiltonian that's simultaneously hopping the clock and hopping the computational state through the sequence of ones you get from the circuit. So just to make some notation, here's like that sequence of states. We start, for example, with all zeros. We apply the first gate, H1, apply the first two gates, H2, and so on. And H is hopping through these. So if you think what happens when you apply this Hamiltonian to a given state with T written in the register and HT here, you get a linear combination of the state before, the clock matching what you have, and the state after and what you have currently. So if you write this out as a matrix, it just looks like this. You can think of it as a discretization of the Laplacian of one-dimensional space. So, and more precisely, so if you took like the limit of this number of gates in your circuit going to infinity, then you could think of this 1 over G as being like a lattice spacing for some discretized Laplacian on the unit interval. This would be really converging to the continuum second derivative in one dimension. So then for the dynamics of this, computer, it's described within this computational space that it's moving in. It's described by something that's effectively just free particle in one dimension, your first problem in undergrad. And so we know something we can do with this Hamiltonian. We can make wave packets, like maybe little Gaussians or something, that have some momentum programmed into them, and they will just propagate down this line. And so at the beginning, you have a superposition where it includes like this initial state, and at the end, you have some superposition that includes this final state where the computation has been finished.
But this is to describe the clock.
So the states down here, so it's describing the two registers together. So this state would be clock is 0, and this is the initial state of the thing, and then the next one would be clock says 1, and this is the first state that you get from the circuit and so on. And so what is the main idea of adapting this, this construction to sort of circumventing these barriers? It's basically just make these wave packets broad. That's basically it. So you can see that if you make these wave packets broad, the broader you make them, the fewer orthogonal states you're traversing as you go across. Maybe you could make this, 1/3 of this length here, so it has to go all the way here before it becomes orthogonal, and then once again. So it's sort of hopping between a constant number of orthogonal states. If you write like what distance through Hilbert space you've gone, it's some constant that's independent of the number of gates you're trying to simulate. And that's kind of how we're circumventing these limits.
Stephen, I know we discussed this before, but I don't remember the answer. I mean, without using the clock construction, why not simply take a superposition over the first t time steps for some t, that's large but small compared to the total length of your computation, and then just keep iterating by one?
Yeah, so well here, since I was really interested in energy, I wanted to do this all with time-independent Hamiltonians.
Okay, good.
So I have some other notes about like discrete,
Yeah, good.
but this was the most pertinent one.
Okay, good.
I'm sorry.
Yeah.
Why is this wave packet efficient to reproduce?
So there's two obvious problems with this construction, which have a solution I'll give you on the next slide. So first of all, if you look at this broad wave packet, it's a superposition over a lot of states in which a lot of the computation has already been done. If you assume that as the starting resources, you're really cheating, because a lot of the computation has been done for you. Similarly, at the end, your wave packet is broad and includes a lot of things where, a lot of amplitude where the computation has not been completed, so that lowers your kind of probability of getting what you want. But what you can do is just pad your circuit. So you pad your circuit with, G identity gates at the beginning, then it's G gates long, and then it's G identity gates at the end, and then you simulate this using your Feynman construction, so that this initial state is only a superposition over different values in the clock register, and the computational register is just all zeros in your initial state. So you're really starting with something that computer scientists sometimes refer to as a fiducial initial state, something that doesn't have computation already built into it. So then you can ask, how physical is this Hamiltonian? First of all, does it involve many-body interactions? Is it, something kind of crazy like that? And, well, what you can do, I believe this trick is from Kitaev, says that, well, if you encode your clock in unary, then this Hamiltonian ends up only being 4-qubit interactions, which is, by my standards, pretty physical. So it's not involving many interactions. You could also say, well, but what about geometric locality? Maybe that's something you want to demand too. If you start adding more and more physical constraints, can you finally rule out these sort of weird looking counterexamples? But actually that's not sufficient either. You can make this spatially local in 2 dimensions. And basically a way you can do that is think about your gates consisting in layers and putting a copy of all the qubits for each layer. So what you do is you can have your clock qubits kind of snaked in like this. So these this little kind of wave packet is following down like this and modifying qubits as it goes along and then swapping them into the next column. So this actually I discovered is an old trick previously discovered by Daniel Naga. So it's spatially local. It doesn't involve many body interactions, but it's nevertheless circumvents this energy limitation. So I think I'm about out of time, and I'll kind of summarize and wrap it up. So the basic premise was that simulation is kind of our way of comparing different models of computation, how we line up our yardsticks against each other. In the QFT case, we asked, well, can QFTs give us exponentially more power than what quantum computers have? Does it go beyond this complexity class BQP? And in the examples we've looked at so far, we see no evidence of that. In fact, these things can be simulated by quantum computers efficiently, but also conversely, that if this QFT is just barely rich enough, even a pretty simple QFT can support universal computation. Then, of course, a question I am very interested to hear from you about is, well, what about quantum gravity models? Do any of those give you plausible extensions beyond standard quantum computing? I think it's a very exciting question. And then the second part is, well, forgetting about using fewer operations, can we just run them faster? Well, contrary to an argument that's been repeated a lot for quite a few years, energy alone doesn't really pose a limit to speed, but that doesn't mean there are no limits. And in particular, this business of like, okay, how long does it take for information to travel at the speed of light between the different qubits is a very obvious one. So I hope to have lots of discussions about all this in the coffee breaks, and thank you for your attention. Yeah.
Well, if these gates or this Hamiltonian isn't perfect, and you think it's ideally similar to a one-dimensional propagation, is there a localization problem if it's a little noisy? Or can you beat that with a broad-enough Gaussian?
Well, I think that's a very valid thing to worry about. We don't have something analogous to like the threshold theorem for these kind of ballistic models. So, you know, maybe you could, you know, it's kind of a, I think, a pretty difficult open question to say, you know, these kind of counterexamples, these kind of constructions I've shown, can you make them fault tolerant? I don't know.
Just so I understand correctly, I mean, even without your construction, when you were cycling through orthogonal states, you could still speed up a computation arbitrarily if you believe that you could pump an unlimited amount of energy into your system.
Yeah.
But what you're saying is that even at fixed energy, you know, you could speed things up arbitrarily in principle, except that then what becomes the dominant concern is not the sort of energy by itself, but the, you know, sort of energy plus the, you know, the Bekenstein bound.
Yeah, something like that.
Tells you that well, wait a minute, but you're still staying at the same amount of energy, but somehow as you would run the computation faster and faster, that same amount of energy would require more
Well,
and more
so there's
volume.
actually
Is that what you're
a
saying?
subtlety there, because
Okay.
like you might say, well, okay, so you can always multiply your Hamiltonian by
Yeah.
x and divide your time by x and do the same
Yeah,
stuff.
right.
But you can say, all right, well, maybe we have these four-body local terms, and maybe we say the coefficient in each of those has to be order 1 by physical considerations. And then the exact statement of what you can do is not so much that for fixed energy you go faster and faster. It's more like for fixed speed you can use less and less energy by using these constructions. In fact, there's two different constructions, and the exact right way to phrase it is not identical for both. But that's why I was careful to say it is like the ratio of clock speed to energy can be made arbitrarily large. Like if you think about, well, how,
I see.
yeah, okay.
So I guess in some physical instantiation, the gates have mass. And so I wonder if we say the interaction energy is essentially 0, if we can bound the smallest amount of mass of a computational unit by saying that nothing can go faster than the black hole.
Yeah, that's very interesting. Yeah, okay. Let's think about that.
All right,
Okay.
let's thank Stephen again.